Okay, so the next thing we're going to do is get a start on Module 3, and we're going to be looking here at the beginnings of Chapter 13 and then also the beginning of Chapter 17. Okay, so if we look here at our learning plan, you're going to notice that we are going to be doing portions of each one of those chapters. So the first part here tonight that we're going to look at is the beginning of chapter 13. And then we're going to have two practice problems slash sample problems that will be working through the examples from the book. Then we're going to be moving on to 17, and then we'll have three practice problems from over there. And as you know, you always have application problems, and you're going to notice that the application problems, you're going to have, looks like four from chapter 13 and then three from chapter 17. So the practice problems are going to help for us to prepare for those. So that's kind of looking at overall Module 3. So let's take a peek at the PowerPoint presentation for Module 3 slash Chapter 13, the first part here. All right. So in Chapter 13, we're going to be looking at energy and momentum methods. And at the beginning here, up until this point, we have been looking at really what are the forces doing to the motion of a particle? And we can look at it in terms of summing these forces is equal to mass times acceleration, kind of the linear translational, or we can look at it in rotational sense where we had the moments and then we were looking at the rotational inertia effects on the motion as well. Now what we're going to find is, I'm going to scooch down here because I actually like this slide a little bit better. So over on the left-hand side here, Module 2 was all about what are the forces? What are the accelerations that we're trying to find? Or we're given forces and accelerations to try to find something. And we could use that Newton's law. Sum of the forces is equal to mass times acceleration, and the sum of the moments is equal to the moment of inertia times the angular acceleration and how that affected things rotationally. Now we're going to start looking at problems where we might be given or interested in velocities, displacements, distances, okay? And in that case, we can use the work energy theorem. So from physics, you probably remember that if there is work that is done on a body, that means there was a change in the kinetic energy. Do you guys remember that from physics? Okay, so we're going to use that principle to help us with problems like this. Okay, so when a rigid body moves from one condition or state to another, so we're kind of looking at those befores or starts and then afters or finishes. Okay, and when we do that under the action of another force or moment, okay, the work done on that rigid body is equal to the change in the kinetic energy that occurs. Okay, now for my entire existence up until last year, whenever I had a kinetic energy problem, I would use KE, right, is equal to 1/2 mv squared. I don't know why, but this book uses the quantity capital T. To me, that's torque, but in here it's T. So you're going to find that here in this book, our equation, the work energy theorem, is going to be the initial kinetic energy, T1, or in state 1, is going to be equal to 1/2 mv squared, okay? But then we're going to take that plus the work that is done over, or from that beginning to end, okay? And they're using the variable capital U for work, okay? Something to get used to. Please do not use K, E, and W, okay? Please do not use K, E, and W. I've got 17 people's work I have to correct, so I need all the variables to be consistent, and I've now done the mind shift to T and U, okay? We'll be adding an extra one here in a little while in chapter 17 that I'm like, what? But anyway, so T2 then is going to be the kinetic energy in the second state or in the after state, if you would, still being 1/2 mv squared. So the equations themselves are similar. The variables have shifted to a little bit different in this book, and we will go with what the book is using. So please do use the variables here. Then the next slide here looks at power and efficiency. So power is the rate at which we do work. So how fast do we actually do work? I like the example of, let's say I'm carrying, a box that is filled with, I don't know, towels, I don't know, laundry, I don't know, a laundry basket, and we're taking it up a flight of stairs, okay? And I think you all can relate to this. If you walk up the stairs, you might get up to the top and you're slightly winded because of the work or the power that you exerted, if you would. Because you did work on that basket, you rose it up a certain height, and you had to, expend energy, or you actually used power to do that. Now, if you, instead of walking up the stairs, you ran up the stairs with the same laundry basket of laundry, you probably get to the top and you're quite winded and very tired. Okay. And that is because you did the same amount of work, but in a shorter amount of time, which required more power. Okay. That's really kind of what power is. All right. So it's how fast do we do work? And the faster we do it, the more power you need in order to do it. So many times we're going to see it as work, U, 1 to 2, divided by the amount of time it took us to do that work. Or we can also see it as force times velocity is another version of power that we can use. Now, the units for power are going to be, in English units, it's going to, I'm sorry, in metric units, it's going to be the watt, which is a joule per second, or kilowatts, you might have heard before. And then in English terms, it's going to be horsepower, which is 550 pound-feet per second. Okay. And then you'll also notice that a watt is 700, that's also 746 watts. So if you need to convert between the two. So watts and horsepower are the units that we see for power in the metric and then in the English units. And then lastly, there's an equation here for efficiency. Efficiency really just looks at how much usable work do we get out of something for what we put in. So it's going to be the amount of output work or power that we get out divided by how much we actually put in. Now, this value for efficiency can never be over 100%, okay? Because we know by the conservation of energy law that we cannot get anything more out of something than what we put in. There are losses that occur. So we can get higher efficiencies than 90%, but we're never going to get 100 or more, okay? Right? So there will always be some sort of losses. Now, before we look at our sample problem 13.1, we're going to do what we always do. We're going to kind of review and get some equations down that are going to help us not only in the practice problems, but also the application problems that you are going to be doing. So I'm going to go underneath my camera and we're going to review the items that we want to add to our sheet here that are going to be helpful. So I am going to refer to this as Module 3, Chapter 13, Equations, okay? Now, I was able, as I kind of look at my sheet here, because Module 3 covers not only Chapter 13, but also 17, what I did is, I'm going to just kind of show you in review how I have this. So I've got the first, I'm going to say half. The top half here is going to be Chapter 13 stuff, okay? Then down below here, this is going to be like Module 3 stuff applying to both. You don't have to write this down yet. Just want to kind of give you an idea. And then the backside, almost the entire backside, is going to be my Chapter 17. So there's more equations here for 17. So I just want you to know sometimes students want to kind of, see where it's at. So if you want to try to keep it on one sheet, I was able to, but again, about half of a piece of paper is what 13 is going to be, and then we'll add to it if you wanted to for 17. I've got basically one sheet, probably usually front and back for Module 1, Module 2, now Module 3, and such, okay? And I don't know if you're using that very same thing, but just for your reference. So, whoopsie, what the heck? So the first variable that we're going to look at here is going to be U, which is going to be our work, okay, is equal to force times distance, okay, force times distance. And then over here, I'm going to just have a little running column where I say what each thing is. So U is going to be work. The reason I think, and you know what, I had always kind of cautioned against this as well. When you would use W as work, capital W, it's also the abbreviation for a watt. Okay. So I would have my students write out watts and then use W as work. So maybe that's why they chose to choose a different variable so that you wouldn't get mixed up with the units and the variable, you know, when you're in equations. So force and distance. So our units can be, for instance, pound feet, right? Force times distance, or they can be Newton times meters. And a Newton meter, when we're in the metric system, a Newton meter is a joule. Okay, so you'll probably be given like work or energy in terms of joules. That is a Newton meter. Okay. Now, down below, we're going to use kinetic energy. Okay, kinetic energy is capital T. Capital T is equal to 1/2 mv squared. Okay, mv squared. So here I am going to be in pound feet. Okay, because do you want me to expand it out? This is a kilogram. This is a feet per second squared. So you have a kilogram feet per second squared is going to be the pound, and then times feet. There's an extra foot left over. Okay. Then we've got a Newton times meters, and that's going to be again a joule. Okay. Now it makes sense that work and kinetic energy have the same units because, as we're going to see next in the work energy theorem, they're set equal to each other in the equation. So work energy theorem. Okay. We're going to say that work is done when we have a change in kinetic energy. All right. So we're going to say T2 minus T1 is equal to work from state 1 to 2. So your ones are like your befores or your initials, and your twos are like your afters or the end or the finish, if you would. Okay. Now, we're going to see that we rearrange this many times for the purposes of the problems that we look at and how the book works them is going to be T1. I'm going to move it to the other side, plus the work is equal to T2. Okay. Now, if something is starting from rest, that T1 goes to 0 because that would be a velocity of 0 that you're starting with. Or if you're moving and you're coming to a stop, then T2 will be 0. Okay. So just so you kind of know. Right. So if I go back up on the top here and kind of catch myself up with my units here, F is force. I forgot about those. D is distance. And we have those units up over here. T is equal to kinetic energy. M is our mass, as we know. Lowercase v is velocity. U is work. Okay, we've got them. Okay. I just wanted to be sure we had each one. Now we did have power in our presentation, so we're going to add that here. Power, capital P, is equal to work divided by time. So however much work that was done in the amount of time that it takes to do that. So P is equal to power. I continue to use capital P. The book uses just the word power, but I'm just use capital P. It's totally fine. And then that can also be equal to F, or force times velocity. Okay. Now here, the units for power are horsepower, which we know to be equal to 550 pound feet per second. Okay. or it's going to be a watt, which is equal to a joule per second. Joule, that's a J on top there. Okay. And those are the equations for chapter 13. All of which, besides the variables being a little different, should be familiar from physics. Okay. All right. Any questions here? All right. So kind of with that, what we're going to do is we're going to look at our first sample problem or practice problem, and then we'll reference our sheet here, as we need to. Okay. So our first practice problem is going to be sample problem 13-1, which is found on page 809 in your book. Okay, 809 in your book. Now, I'm going to look here at the PowerPoint presentation because I think it's a little bit more clear than looking underneath the camera. But what we have here is we have an automobile. It weighs 4,000 pounds and it's driven down a 5-degree incline at a speed of 60 miles per hour. When the brakes are applied, causing a constant total braking force of 1,500 pounds. Determine the distance traveled by that automobile as it comes to a stop. Okay? All right. So what we're going to do is we're going to put this aside and we are going to create our problem, givens, finds, and then talk about how we'll proceed. So this is sample problem 13.1, page 809. Okay. I'm going to put our standard convention in the upper left-hand corner or upper right-hand corner, and our givens, okay, are the weight of our automobile, 4,000 pounds. The velocity 1, this is what it's going at currently, okay, before it applies the brakes, and that's going to be 60 miles per hour. And then the braking force is going to be 1,500 pounds, which means that this is a constant acceleration state, okay? Constant acceleration. What they want us to do is they want us to find the braking distance, okay? That distance that we're going to travel while we're braking, okay, to a stop. Now, since we're solving for distance, we are going to use that work energy theorem, okay? So we're trying to find a distance. If you remember, I'll go back over here. If we go back a couple slides, remember this one right here, we want to find a distance or a displacement, all right? We are given a velocity, so the work energy theorem is a good place to start. Sometimes you're like, where do I start, right? And this is kind of one of those things. It's considered an approach that we're going to use. So our approach is going to be the work energy theorem. So I'm just going to write here T1 plus the work 1 to 2, U 1 to 2 is equal to T2, or the kinetic energy after, okay? So we're going to be solving for a distance. So we're going to use this work energy theorem, okay? Now, we need to find the values for, each one of these variables. So we're going to start with our kinetic energy, okay? Our kinetic energy 1 and our kinetic energy 2, okay? You could start with work if you wanted to, honestly. Really doesn't make a difference. Okay. So kinetic energy. So we'll start with, if you would, position 1, like as we're starting. So T1 is going to be equal to 1/2 mv1 squared. Okay, fv1 squared, mv1 squared. Now, our velocity, number 1, is in 60 miles per hour. okay? We're in English units, so we need to have everything in feet and seconds. So we need to convert that 60 miles per hour to feet per second, okay? So over on the side here, I'm just going to do V1 is equal to 60 miles per hour, and we'll do our conversion of, I'm going to do my miles first, 1 mile on the bottom, 5,280 feet. And then we know that 1 hour is equal to 3,600 seconds. So hours cancel, miles cancel. I'm left with feet per second. My V1 should be equal to 88 feet per second. So make sure you get that number. Okay. Now we also know that mass in English units is going to be weight divided by gravity. Okay, so we'll put that right into the equation. It's not a hard one to stick in there. So that means that we're going to have 1/2 times weight divided by gravity. It's going to be 4,000 divided by 32.2 feet per second squared. I didn't write it up there, but don't forget. And then it's going to be 88 squared. Don't forget to square that. That's another easy one to forget. Okay. So your T1 should come out to be 480,994 pound-feet. Okay. So we can put our little, this is our first kinetic energy. Okay. Then for T2, okay, the after kinetic energy. So T2 still going to be equal to 1/2 mv2 squared, okay? Now, we're going to come to a stop, right? We're putting the brakes on. So this goes to 0, T2 is equal to 0. All right, that makes it simple because we're coming to a stop. So we're starting at 60 miles per hour, we're going to put the brakes on, and then we're going to come to a stop. All right. So that's these two variables we're done with. Okay. So step number, I'm going to call it step number 2, is going to be the work. Okay. The work is going to be the U1 to 2. Okay. U1 to 2 is equal to force times distance, right? Force times distance. And that's going to be a plus or a minus F times D. Oopsie, let me move that up. Now, let's draw a little diagram, okay? Because we got to see what forces we have going on. At least I do. So I'm going to exaggerate the 5-degree incline, okay, just so that we can see a little bit more of a difference. And I'll draw my little, I'm not going to draw an automobile, but I'm just going to draw a rectangle up here with a center of gravity. Okay. And coming down from that center of gravity is going to be the weight of 4,000 pounds. Okay. And this angle is 5 degrees, not 55 degrees. Okay. We also know that there's a braking force. So the car is going down the incline, okay? So we're going to say going in a positive direction is going to be going down the incline. The braking force is impeding that motion. So this is going to be the FB, which is equal to 1,500 pounds, right? We also have a normal force, okay? That normal force, which is a support force, is right here. Okay, so that's another force that is on this. Now, as we look at this direction of, if you would, the incline, okay, we have a force, if you would, as a component due to the weight of the car. So if this is going down, and if I draw through here kind of a y-axis, if this is my x-axis along here, okay? And if I draw then crossing that, my component going down the incline, do you see how that is the force going down, which would be a component, if you would, of the weight coming down? Do you see that? And then if we go over this way, there would be another component that would be equal to the normal, okay? But we're interested in this one right here because this is the motion part, right? This is the direction that motion is happening. So we're going to call this FW. It's kind of like the force due to the weight. And that's going to be equal to, so if this is 5 degrees here, do you see how this is 5 degrees right here? Okay. And that would be the side opposite. So this would be the sine of 5 degrees. Ah, shoots. Sorry, I'm going to put it down here where there's more room. So FW is going to be equal to the sine of 5 degrees times 4,000 pounds, which is the hypotenuse of that triangle. Okay. So FW down here, this one right here, is going to be 348.6 pounds. Okay. Now, this is the direction that motion is happening. So this is where work is happening as well. So 1,500, that is impeding motion, and it is pointing up and to the left. Our positive direction is down and to the right. Okay. So that means we're going to have a negative 1,500 times the D distance. That's going to be our stopping distance. Okay. Plus the force FW, which is 348.6 times D. Sorry, trying to get this all in there. There we go. So this is my FW, and this is FB, the braking force. Okay. So now we can combine those and solve for D, or put it in terms of D. So our work 1-2 is going to be equal to a negative 1151.1 times D. Okay. So now this is as far as we can go, and we'll plug that into the middle of that. So going back to that work energy theorem, T1 is T1 plus U1 to 2 is equal to T2. My T1 from up here was 480,994. My work right here, that was a negative 1,151.1 times D, equal to 0. That's T2. So now solving for D. Go ahead and do the combining and such. You should get, in the end, 418 feet. Make sure you can get that number. That is going to be the braking distance for our car. Okay. Any questions on this problem? So starting out with our givens, right, up on the top here, deciding that we're going to be using the work energy theorem, then each one of the components here, the two kinetic energies and the work, then we solved the kinetic energy before, kinetic energy after, and then the work during, and then plugging those in and solving for, in this case, the unknown of the braking distance. Okay. All right. I am going to stop our recording here.